Hello guys, welcome back to my YouTube channel. My name is Mike Matthew KE and this is my Logic in Programming series. So today we are going to build an AI for our tic-tac-toe game. So if you look at the link up there, last time we did tic-tac-toe, developing the game from start to finish in Python, and today we are going to now build an AI for that game. Now, when it comes to building an AI, there are several methods that you can use. You can look at the minimax method, for example, but for today, we're going to use the qtable method, right? So, for today, we are going to use ChatGPT to help us in getting the explanations of these definitions, right? And we're going to be looking at that directly. Also, it will help us in knowing how we need to implement our logic. So, ideally, whenever you're using AI and this in this world of AI, it is always good to use it in a way because it's still the future of our programming. But in my way of using, I prefer to understand fully how it works rather than using it to do my code. So in this case, we'll be looking at the definitions of the qtable, how it should be implemented per se, and then now we'll try to implement that in our own code. So let's dive right in. So this is the code we had last time, but I'm going to switch on to this where I asked ChatGPT to explain what a qtable is and how I can use it in a game of tic-tac-toe. So, by definition, a qtable is a core concept in Q-learning, a type of reinforcement learning. So that's basically what we're going to do today. And it's essentially a table that tells an agent what action to take in a given state in order to maximize long-term reward. So if I can explain the concept of reinforcement learning in a few words, it's kind of like when you're teaching a child what to do. So if the child does something wrong, then they get a punishment, maybe a timeout or something like that. And if they do something right, then they get a reward, let's say a sweet or something like that. So that's what reinforcement learning is. It's rewarding the good things that you do and then punishing, in quotes, the wrong things that you do, right? So here, when we're using this qtable, how can we use it? So what is a qtable in the first place? So a qtable is a 2D table or dictionary where rows represent states and columns represent actions. So in this case, we're going to use our qtable as a dictionary rather than a table as explained here. So our state is basically our 3x3 board. Like what is the state of the board right now? Where are all the pieces that are currently active or filled, and who has filled that position at the moment? That's our current state of the board. And then our action is what step are we taking next, right? So if it's X and O, then maybe it's O's turn. So what step is O going to take? That will be the action that we're doing. Then how Q-learning works, I think I've kind of explained it in a way. But essentially, when you're training the qtable, you'll initialize it with a 0, and then the agent explores and plays the game. So ideally, what we'll do is we'll let the game either play with itself or play against a person. So as these moves are being done, it will keep learning from it. And so the value, if you can see up here, we say that the value q state action. So q is kind of like a, let's say it's a function, right? That evaluates the state and action. So the value q state and action represents the agent's estimate of the expected reward for taking a certain action in a given state. I hope that is self-explanatory. Then here, so we have QSA. So for a certain action, how do you get the value of a certain action? So first you take the original value. So as you've said, the original value is usually 0. And then we add now this formula right here. So where the alpha is the action taken, right? The action taken, and then R is the reward received. We'll see how rewards are given in the long run. And then we have lambda, that's the discount factor, how much the rewards matter, right? So um, if it's in the case of, let's say it's a child that you're rewarding, then how many sweets do we give this child to show that we are rewarding this good behavior, right? So you can decide to give the child 10 sweets, or you can decide to give the child maybe one sweet, right? Then we have the maximum. So this is a function of the maximum q, where spline, this will be the new state of action, and then minus the current state of action. So this kind of looks a bit complicated, but perhaps what we can do, we can ask ChatGPT to define this in a simpler term, right? However, when you look at this, when you're using a Qtable in tic-tac-toe, so you define the state of which I've explained. So for example, the state XOXO, so this explains how you represent a board, for example, in a string. And then you define the actions. So each action is a number from 0 to 8, representing a position on the board, right? That's one way you can do it. And then you can use a Python dictionary where you have that Qtable. So each time the agent plays, you pick a move, play the move, observe the reward and the next state, and then update now your Qtable with the value of the state and action, right? So the reward scheme, for example, if it's a win, you get a +1. If it's a loss, you get a -1. And if it's a draw, you get a 0.5 or a 0. For this case, I'll be using 0. If it's an invalid move, I'll use a large negative. In this case, I'll not do the section for the invalid move. I'll expect the code that we did last time allows us to prevent the invalid moves from happening. So I'll not cover the invalid moves in this video, right? So here's an example of what they're giving, but it's simplified, so I'll just leave that be. So now that you have a kind of overview of what a Qtable is, then we can start implementing, and then in case we reach a roadblock, then we can go back and research a bit more of how we can implement it, right? So going back into our code, so like we had last time, this is the code that we had. So if I just run it, we can see the sample that we had. So you click to play. So at the moment, it's just one person who can play. It's just against two people since we don't have an AI, right? So you can just replay every time. Let's make sure O wins this time, right? O has won, so it can be winning in any way. And so in order to implement this, let's start with creating a different file for our AI, right? So I'll just create a file and I'll call it ai.py. I know it's not the most the most creative of names, yeah, but here we can create a class that we'll call AI, right? So in this class, what we need first of all is that Qtable. We'll need that Qtable first of all, and then we'll also need to initialize our state. So in our constructor right here, what you can do, actually we'll define this Qtable within the constructor. So that's part of the class. So self.Qtable will be equals to an empty dictionary, right? What else do we need to define for this? In the future, this Qtable we'll probably save this Qtable in a file, maybe a JSON file, because since we're doing a dictionary, we can do it in a JSON file. If you don't know what a JSON file, it's basically a way to store data. it's a way to represent a dictionary in a file. That's basically what a JSON is, right? So we'll probably use that in the future. For now, let's just initialize to an empty qtable. Then the next thing we'll do is, so we need to be able to represent this board in a string, right? So if I go back to the sample that we have here, you can see here we have x0 x blah 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 blah. That represents how the board is in the in a string format, right? So in this case, I'll just create a function that allows us to let's say stringify the state of the board. So get board state, right? So that will be a function. Of course, it will take self, and then from here, so what will we pass as the board state? So we can see here that our board is a 3 by 3 matrix, right? Or rather, a list within a list. So I'll expect here to also get the board state, which is actually a list. So this is a list within a list. Maybe I can just define it as so, a list within a list. I'll not define the size, but in our implementation now, we'll try to represent this as a string. And how we can do that? So we can just represent it as, let's call it state, as an empty string, and then we'll just loop through each type of list. So for x in board, then for y in x, what we'll do is we'll represent the state is equals to, well, now from here, how do we write? Okay, ideally what we'll do is we'll add to this state so that we represent it as something linear. So how do we represent this? So originally, if you remember correctly, we have a none representing when we don't have any x or o represented there, and then whenever we have an x or an o, it will be placed on that position, right? So so what we'll do here, if the state is empty, or rather, let me say if not state, basically meaning we have a none value, then what we'll do is we'll give the state as so let's give the state as a hyphen, okay? That will represent our blank state. Nothing has been put there, right, in that box. And otherwise, if we have a normal state, so now in this case we can represent it as x and o. However, I would like to represent it differently. So when it comes to this other section, I would like to represent it differently, where I'd like 1 to represent when we have the AI and 0 to represent when we don't have the AI, right? Rather than representing it as x and 0, or rather o, x and o. That way, whether the AI is o or x, it won't matter. It will still be able to know who is the AI and who is not. So in this case, I would definitely need to know what value the AI has been assigned. Is the AI an X or an O? So so we'll give in our initializing state, we'll give the value representation, right, which we expect to be a string, and then we'll pass self dot value rep is equals to value rep, right? So that's our value representation, basically array x or array o. And so when we come here, what we'll do is if the if the value rep matches, so if our value rep matches here, so self.value rep is equals to the state, right? Basically meaning we're representing the current state of the AI. So if it's X, then right now we are writing something that X has, the AI has represented. I hope that makes sense and is not confusing at all. So basically we'll give the state as 1, right? Otherwise, if it's not this AI that has played, then we'll give the state as a 0, right? So that's how we represent the board state. And then once we've done this, we can return the value of state. So that's how we present our board state, right? So let's give an example. So for example, if let me just give an example here. So if I do AI dot, if I create an AI here, for example, this will be our test case. And then I want to get the board state. AI.get board state of, for example, when we have, so let's represent this like so, right? So let's say we have none, we have none, we have X, then we have O, right? Then the next maybe have none, 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 and I'll just duplicate this. So let's say, for example, this is the state of the board. So how will this appear as a state? So I'll just print this right here and run this. Looks like we have, oh right, we need to pass our value rep here. So our value rep, let's say X is the state of, X is representing the AI right now. So if we run this, you can see that we have, oh, this did not come out exactly as expected. Right, so what we've done here is if not state, then state is, otherwise we'll have the value rep, if value rep is equals to state. Well, here we have something not working correctly, right? So we're expecting that we'll have a lot of dashes to represent the none. Okay, right. Now I know what we've done wrong. So in this case, we're supposed to be looking at the value of y, right? So here, if it's supposed to be if not y, then we give that state. Else, if value rep is equals to y, then we put that, right? So that's an error on my part. So if I run this now, then we can see this will be the representation that we get, right? So that's some live debugging that we've done right there. So now this is how we represent it. Of course, we'll always have 9 values representing the state of our board. And if, for example, I add, let's say we have X played here as well. If we run this, you can see that now we have, so 1 will always represent the AI, the player that is represented by the AI, and 0 will always represent the other player, right? So that's what we mean by board state. So the next thing we'll need here is basically what move will our AI now play, right? So definitely we need to be able to return to the main game. This is the move that the AI has played, right? So we'll have our function for get move, which will basically be our main function, right? When we're using it on the side of the main game. So we have get move, and in this case, of course, we need to pass the board state, right? Again. realize this is repeating very often. So when you're getting a move, so the idea is we need to get the best possible move that we can play in order to win, right? So what can we do in that regard? Um, so ideally here, what we can do is, since we have all our possible actions, that's fast. We have all our possible actions, so we can look from these possible actions which has the best reward, right? That's basically what we need to be able to do. And in order to do this, uh, basically we need to get the possible actions first of all. So possible actions will come as get possible actions. So that just makes it simpler since we've put it into a function. And all you need to do is pass the board. Sorry, this has to be self dot, right? Get possible actions, and then we pass the board. Then from this here, right, we also need to get which of this has the best state, right? So I'd like to separate this into a different function as well. Get best state, right? So again, itself, I'll expect it to take a board, and I'll expect it to take the possible actions. Right? So from all these possible actions, which is the best, or rather, actually, instead of best state, let's get the best action, which is the best action that you can have, right? So in our board, we have all these states, and we need to check which one, which action will give us the best value, right? So if I can just look back at this example, right? Okay, well, it's not represented here. So if you can just look at this example here. So for example, this is our current state. So we have all these possible actions, and ideally, when you're looking at, so for example, if I place this in a Q table, right? So what we expect a Q table to look like is this is our state, and the action, for example, is 0.1. Now, for example, and then maybe we have another state again. Then we have 0.3, right? So this is our previous state, right? So maybe placing this here and placing 1 here, maybe this has 0.1, which means it has a better chance, and this has 0.3. So basically, we are looking at which of these states, or rather, which of these actions, these possible actions that we have, will give us the best value out of our Q table, right? So that's basically what this function is supposed to do. And that's basically the whole point of getting the next move. Actually, I'll just update this function to get next move, right? So in this case, what we'll do is we'll loop through each possible actions. For action in possible actions, right? What we'll do is we'll get the value of performing this action. So that's basically, this is our Q table, right? So in our Q table, we need to find the action, the result of performing this action. And remember, we already have this function here, get action state, right? Which will give us the state of the predicted state of our action. So when we do get action state here, we pass our board. I keep forgetting to put this self. So we have our board, and now we have our action, right? So we need to get this state that we are expecting to get, we get the value from our Q table, right? And then we need to check if this is the best possible action, right? So what I can do is, let's see, what can we do? So we can have what is our best action value at the moment. So we just give -1. -1 is the worst value that you can get, right? So our best action at the moment is -1. And then what we'll do is, if the value that we'll get from our Q table is greater than our best action yet, then it means that this current action is the best action. So actually I'll change this to best value, right? So that our best action is actually represented as will actually be represented as a tuple, right? Best action will be represented as a tuple, right? Of which we'll not initialize this one, but in that case we'll come, actually let me just give it a value of none. We'll initialize it as none. And then for our Q table, when we come here, we'll give the if now this is our best value, so we'll assign best value is equal to this. Actually what I'll do, I'll just separate this into an actual state. So action value, and then put it that way. So the value that you'll get once you perform this action is that. So now if our action value is greater than our best value, then now our action value our best value becomes this action value, and our best action becomes action, right? So basically what this will mean is we'll evaluate every possible action that we have, and then from these possible actions we'll see which one will give us the best value from our Q table. Once we get our best value, that is what we'll give back as our best action. So here we'll return our best action, right? So that gives us the best action, and ideally what we'll have to do here in getting our next move, we'll just return our best action, right? That would be self.getBestAction right here, and I'll just pass in the board and the possible actions that we have. As simple as that, right? So now we have our way to represent our next move. So now our biggest issue remains, how do we fill our Q table, right? We have initialized an empty Q table right over here in our init function. So first of all, how do we update this Q table so that it has values? Basically, how do we train our AI, right? So in that case, what we'll do is, since we'll be updating our Q table as the AI is playing, what we'll do here is, let's have a boolean of whether we are training or not, right? So train, are we training? So by default I'll put it as false, right? So that we are not training our AI all the time. And then I'll give self.train is equals to the value that we've given here, right? So now whenever we are performing our next move, right, because we'll be training the AI as it is playing. So the first thing we'll do here when we're trying to get our next move is we check if we are training. If we are training, then we need to check whether we have the current move that is on the board, whether it is represented, right? So if that's the case, then we'll check what is our current state in the board. Self.get get board state, right? Which will pass our board. And when you get the board state, I'll make this current state. Actually, you might need this outside of training, so let me just put it out there. So in case we are training, then we need to check if we have this current state represented in our board, right? So if current state in qtable, self.qtable dot keys. So keys will represent, basically, since it's a key value pair, so keys will give us a list of all these states. So if we have the state represented, or rather we're actually not interested in if the state is there. Instead, we'll just have if the current state is not present, then what we'll do is we'll add this current state to our qtable. We'll add this current state right here to our qtable. So that will be like so. We add the current state, and this is equals to 0. So we'll have our initial value represented as 0. So I'll just maybe I can just define that over here. So initial state equals 0. So I won't need to keep looking for that. Actually, this should be initial state value. Let's make sure our variables make sense, and also remember this is an integer as well, right? So coming back here, instead of passing this, we'll pass initial state, self dot initial state value, right? Like so. So now every time we encounter a new state, we'll give it an initial state value of 0. Now another thing that we can also do here, so I've just realized that we don't need this current state out here. We'll just state it within this if condition. So another thing here is what happens if, for example, we are trying to make our next move and we don't have that possible action represented, right? So what do you do then? So whenever we're getting our best action, we also need to check whether we have our current state within or rather the predicted state within the board, right? So in this action value, we also need to check whether this action value is in our qtable. Why? Because we are also trying to represent, we're also trying to get actions that are available for us, or rather we know the value of that action. So in this case, I'll come here and I'll separate this. So action state, I'll put it as action state is equals to this. So whenever we get our action state, we also need to check, so I'll just return action state here as well. So since here we're trying to access our value in the qtable, we also need to make sure that we have this action state available in the qtable so that we are able to access it. So in this case, what we'll do is if action state in, or rather we are interested in if not action state in self.qtable.keys. So basically the same thing that we have below there, we'll basically initialize again. We'll update the qtable here so that we have self.qtable is equal to self dot initial state value, right? Like so. So now there we go. We have our best action. So what do we do from here? So if in the case where we have our action state, now we'll never encounter an issue where we are trying to access a value but it has not been assigned. So given we are giving our state value as 0, we can play with that. Now the next thing we can do now is, given you're trying to train our model, that this update will not need to be done only when you're training. I think this will need to be done at every turn. In case there's a new state, we need to represent it in the board and give it an initial value. Then what we can do now is we can train. How do we train our So now we need a way to update our Qtable in terms of value rather than adding states. So at the moment we are adding states, right? And we're initializing the state value to 0. But we also need a way to update our Qtable. So this now will be our function update Qtable. And in this case, what we'll need is our board, which is a list of lists. And then what else will we need in our Qtable? I believe the rest is available for us. No, we also need our reward, right? We need to know whether whatever move we've done has made an impact, right? So maybe we have won, right? This is our board. This is our reward. So we need a board. We need the current state of the board. We need the action. We need the current state of the board, and we need the updated state of the board. So basically we need the board, whatever action we've done, and whatever reward that action has given us. Yes, I believe this will be able to represent for us. Then maybe we can look back at this function right here that allows us to update. So what we need is our current state, the action taken, right? The reward received, which we have passed. So for these rewards, I'll just have these values defined somewhere, maybe outside the class. So win state, we have our win state, which is 1. We have our lose state, which is 0, and we have our draw state. Sorry, the lose state will be -1, and we have our draw state, which will be 0. So I'm expecting that these are the states that will pass when we are talking about reward. Actually, let me rename this from win state to reward, so that we make sure every word makes sense, right? So we have our reward right there. So now we have our win reward, our lose reward, and our draw reward. So those are the values that we'll give, and that's what we expect to be passed here as the reward. So this is an integer, and our action is a tuple of integers, right? Oops. A tuple of integers. Now, from this point, going back to our formula, we also have the new state after the action. Of course, since you already have a function defined that will allow us to get the new state, there's no problem with that. But then we also have this value. We have the learning rate, how fast it learns. So how much of the reward is going to impact the value, right? So for this one, I'll just give the value of 0.1. Then we have our discount factor, how much future rewards matter. So for this, I'll need a bit of an explanation. So for the learning rate, I at least know how much we want to change our value, right? So for this one, I believe I'll give a learning rate of 0.1. Right. Actually, I might need a bit of explanation on. I need to understand. Let's see what ChatGPT can understand the learning rate and the discount factor, right? Use examples and explain like a child. Let's see what the ChatGPT will give us with this. So, so this is a scenario that that ChatGPT will give us. So you're learning by playing lots of games. After each move you ask, did that move help me win or lose? And then you update your brain, the Q table, to remember that move better next time. But here's the twist. Two things decide how much you learn and how much you care about your future, right? So the learning rate is how quickly should I trust new information, right? So imagine you're drawing with your crayons. The more pressure you apply, the darker the line. The learning rate is like that pressure. So if you have a high learning rate, then basically you'll adjust your values more based on the new information that you're getting. Okay, that makes a bit of sense. Here with high learning rate, that is 1. That's a high learning rate. Basically, if I win, I trust that information fully. And with a low learning rate, I'll give 0.1. Okay. Okay, nice. So a good balance like 0.3 to 0.7 helps you learn while trusting past experiences. Right. So I think I might take ChatGPT's word on that. So if we look at the discount factor as well, we have gamma. So the discount factor is basically how much do I care about the future. So this, let's say this scenario. So this tells the robot how much future rewards matter compared to rewards right now. So when lambda equals 0, or when a discount factor is 0, you only care about the immediate rewards. Okay. So did this move make me win right now? No, then I don't care. Interesting. If y equals 1, so you care a lot about future wins. This move didn't win now, but maybe it sets up a win later. Aha. Okay, so that also matters. So let's say you're playing and placing an X in the middle. And placing an X in the middle won't help now, but it sets you up to win in 2 more turns. So if y equals 0, no reward, not good, not doing that again. Okay. And if y is 0.9, oh, that is a smart move for the future. I like it. Right. So the discount factor basically tells the AI how much the future matters to me. Right. So a good gamma like 0.9 or 0.95 helps the robot think ahead, not just the next move, but the end of the game. Right. So I hope that helps you understand what discount factor is. It has helped me a lot. So when it comes to discount factor, so these I'll define as states for the AI. So I'll have discount factor, which is an integer. Sorry, this will actually be a float, and I'll give it a 0.9. Oops. So 0.9. So that it really depends, or rather really looks at the future, so that we can find that discount factor. And the other value that we have is forgotten the name that we've given it, the learning rate, right? So the learning rate, so how much do I want my AI to trust any new information? So for example, if it's a win, how much do I want the values to change. So I think I'll give it a 0.5, just since ChatGPT says a good value will be in between 0.3 and 0.7. So I'll just give it a 0.5 so that we can also see how that affects us in the long run, right? So now going back to now the formula. So so you can see here, where's the formula? So our new value for the Q table is, first of all, we get the current value of the current action, right? So if I come back here, or the current value of the board, so current value will be, we get the value of the Q table for the current state. So let me just separate out these variables. So current state is get board state of the board, right? So now we get the current value of the current value of the current state, right? The other thing we'll need as well is the new state, which will be gotten by get action state. Basically, what will be our state once we perform this action. Board, oops. So board and action, and then what will be there? New state value. Let me put it that way. So the new state value will be get the Q table and the value of the new state, right? So those are two factors that we'll need. So the formula says we have the old state, right? So the current state of the board, and then now we have I'll just literally put this into a function. So update value, let me put it that way. So update value is equal to, so we have our current board state, right? So current value, this is the current value that we have, and then we are supposed to add this to, we get our learning rate, right? So self dot learning rate, and then we multiply this to whatever operations that will happen here, where we have R, which is our discount factor. So self dot discount factor, and then we have to add this to, wait a second, this, wait a second, this is supposed to be our action taken. Wait, what? How do you represent action taken? Let me see if this example here maybe can help. What is alpha? Alpha. Oh, that's right. My bad. That was a bit of confusion. So this is not A. This is alpha, which is the learning rate. So I'm on the right track. Then we have R, which is the reward received. Then we have our discount factor, of which we multiply by the maximum. So we have this times the maximum of the new state and action minus. So I believe this will just be the new action that we've taken, right? So basically, this will be, let me just see that one more time. So R is supposed to be the reward received. Okay, that's where I'm getting my confusion. So we have a reward plus our discount factor times, so just put this into a bracket so that we know what we are separating. So we have a discount factor times, so the discount factor times the marks of the action. So basically, what is the value of our action right now? So I'll just use the new state value, and then I'll take minus, this is supposed to be minus the current state value, right? Which is our current value, like so. So this should be the updated value. And if you look at this, this value goes back to the current state, right? So our Q table will be updated with the current state, self.qtable, right? Will be update. Our current state will now be updated to the update value. So that's how that should happen. So depending on the reward, we'll just do our update accordingly. So this will update our Q table, right? And so now we'll be able to have more values being input. So the other thing that maybe we need to add to this, I believe we've covered everything in terms of training the AI, right? So maybe the only thing that will be remaining is how do we save this this Q table, right? So we need to have it saved somewhere. So what I'll do is I'll just have another function. I like to separate things into functions so that we can have these things working out. So first, save table state, save Q table, which will be taking self, and all we need to do is to convert this into a JSON, right? So you just open a file with open, let's call it brain.json, right? In a read format as file. Then we can save the self.qtable. How do you do this? Is it json.dump self.qtable? I think we need to import JSON. It's been a while since I used this, so I believe it's json.dump self.qtable. Let me just confirm what this function actually does. Serialize object as JSON format stream to FP. So direct support a file like object. So what it returns is basically a string. No. So we have our object and then support, right? I am not sure. Yeah, I'll just have to Google this one. So convert JSON into, convert a dictionary into JSON. Just need a memory boost. So it's JSON.dumps, right? It's dumps with an S. Wait, JSON.dumps converts a dictionary to a string object, not a JSON dict, right? So JSON.dump, that will give us a string object, dumps, like so. will give us a string object, and then that's what we'll write to this file. That's how we update our qtable, right? Another thing we might also need is to load the qtable. Def load qtable self, and then what we'll do is I'll just need to confirm how we convert a JSON to dictionary, right? We converted JSON to dictionary in Python, so JSON.loads, right? So what we'll need to do is to get the string first of all. So we'll open the brain.json. So given I've not given this specific directory, I expect it to be going as file. So this time it will be in read mode, and what we do is file.read, right? So we'll read the entire stream, and what we'll do in this case, we'll json.load. Is it load or loads? Oops, loads. So it says loads. So loads file.read, and then what we actually should do is loaded qtable equals that, and then what we'll do is we'll put the self.qtable equals loaded qtable, right? Great, so that's how we'll do it. So what happens if this file doesn't exist, or rather we've not trained? What we can do is we can just if not file.path, sorry, this is supposed to be OS, so I'll also need to import this, import OS, right? So OS dot, I think it's dot path dot, is it exists, and then we give the name of the file. So if we do not have any JSON file or any brain for or qtable defined beforehand, then we can give the loaded qtable as an empty. Otherwise, an empty dictionary. Otherwise, our loaded qtable will be what we load from the JSON file, and then now we put it into a qtable. So up here in our initialize, instead of doing self.qtable, we just do self.load qtable, like so, and that will be able to cover for us in what we need. Great, so I believe now we have a complete working AI. I'll just delete this test code that we've been doing. So let's try to implement this AI right into our code here. So first things first, we need to import, so from AI, import AI class, right? And then what we'll do, so we have our game overview in which, no, this is game overview. We need our game view, right? Which is our main section where we are playing. So what we'll do here, we'll create self.ai, which is equals to, so our AI is equal to AI, right? We initialize that class, and then so there's a boolean I'd put here about train. Right, so this boolean, we've not used this boolean. So whenever we try to update the Q table, we should only update if we are training. So if self dot um, Q table, sorry, self dot train, if we are training, this is not a function. If you are training, then now we can do all this, right? If you are training. Otherwise, we won't need to update the Q table anymore. However, we can just be saving the Q table as we go along, right? Actually, this whole function just needs us to be training the model, right? So in this case, we want train to be true, right? So now we have an AI and we have now our other player, which is us basically. So what I'll do for this is I want to give our AI. Oh, we've not given our AI an action. So let's say we give our AI to be X, right? So value rep. I want our AI to be X and train equals true, right? So in this case, now that we have our AI, actually, let me rename this as something a little bit better, AI player. So now that we have our AI player, what we can do, so in order to get the feedback for that someone has played, we usually had this function. Where is it? On mouse press, we had this on mouse press. We do this action, so that would have allowed us to. That basically allowed us to do. Let me just run this. So whenever we click, we are able to play, right? But now, first of all, if it's the AI's turn, then our clicks should not work, right? So given we've given our AI this value right here. So what I'll do is if our AI player is X, then that means user or user player is O, right? It's not the best defined this way, but I'll just do it this way so that we can start off like that. So now we have our user player, and then when we come to our function right over here, where we now expect the user to input something, then if it is not the player's turn, so remember we have this current player value. If self.current player is equal to the self dot the user player, not current player. So user player is that, then now we can make a move, right? So if self.current player is equal to self the user player, then accept a move. Otherwise, don't try to get any of this. So now if I try to play, you can see that since X is the player that is starting, I cannot make a move simply because I am not the AI, right? So now that we've blocked that, the second thing we can do is now we need to be able to play as an AI. So on update, is all the logic to move. So this is where the main logic happens. It basically happens on every draw call, or rather on every game loop, we'll have this on update function being called. And so what we'll basically do is from here, if our current player if the current player is is not equal to the, or rather let me put is equal to AI player dot value rep, right? So you need to get our value rep. So if the current player is supposed to be the AI, then what are we supposed to do in this case? So we just need to call our next move function, self.next that get, no, not self, sorry, this is AI. So the AI player that get next move, right? And all you have to do is pass the board. And once we do pass the board, what happens in this case? So you can see here we have to update. We have to update just like we did last time. So in this case, what I'll do is where were we? So we are on update. So we have this. So we'll do this update. So the next move, I'll give it same values as this, x grid and y grid is equals to that. Right? So get the next move, and then now we update. That's one, and then so every time we do this, we need to also check if the player has won, right? So if not, the player has won, the change player. So I'm just going to turn off training for now, so that we can also check if our AI is working as expected. So if I run this, we expect that, oh, and boom goes the dynamite. So int object is not subscriptable. So now we have an issue here. This is on line 55 of AI. So it says that this int object is not subscriptable. So get action state, int object is not subscriptable. So I think it's complaining about the action state. So our get action state should be returning the board state, right? So I'm not sure what the issue is here. So we have our action state. So I'm just going to print the action state here and try to recreate the error. I'm not sure where the issue is coming from. So if I think I'll also print our Q table, right? So I can see what's happening in the Q table. Maybe it's an issue of this missing or something like that. Let's see what that brings us. So if I run this one more time, so let's see what happened in our print. So we have, so this is our state that is printed. Then our why did our Q table come as 0? That is crazy. So when you printed our Q table, it came as 0, which means you're not initializing this correctly. So I'll just go back to our init function where we load our Q table. Let's go to definition. So when we load Q table, ideally it should not. So I'm not sure if this happened. Print brain found. I'm thinking it's possible that it tried to initialize something that wasn't there. Let me see. Oops. So it's this side. Uh-huh. So brain found is not. I wonder what it is I'm missing. So you have self.qtable equals loaded qtable. Why is the qtable 0? Why is our qtable 0? I am initializing it, right? Oh, do I need to specify it here? No, I don't think so. So let me print it at this point. And see if I still get the same results. Let me just clear that. Run it one more time. So when I run it, a couple of warnings. AI object has no attribute qtable. Oh. 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 Right. My bad. At this point when I'm printing, it doesn't have the qtable yet. So let me run that one more time. Keyboard. Alright, so it fails. So here we can see that we have So is this a problem of initializing? What? Let me see if I place, I'm not sure. So maybe if I place this right here, because there's something not happening correctly somewhere. Let me see. So once you initialize, and then the next thing we do is get next move. So when we get next move, we update state. So clearly something is going wrong. So let me try to run it with having still the same problem. Interesting. So I need to trace back where this, it seems that, oh, wow. Yeah, this is where the problem is. So at this point, I have actually changed the value of the qtable to 0, which is initial. Okay, so this is where the problem is. And this is really why I don't like the high-level languages. Because you can change the type of the, oh man, it's crazy. So in this place, this is supposed to be, we're supposed to be updating the qtable at the value of the action state and not the qtable itself. So that's where our error is coming from. So let me just remove this print statement since they're not needed. I believe that should clear our issue. So if I run this now, hopefully it's, well, another problem. Wait, what? Oh, here, this is supposed to be best action equals action, right? A few bugs over there. Oh, did you just say X? Whoa. Wait, what? X is 1. That is not correct at all. So I need to see what happened. Because something definitely happened. So let me see. When we go to this update function, So on update, so what I'll do, I'll just print our board, sort of board after every run and see what happens here. So it says X has won. Why? How? Oh, this is not right at all. So something is wrong here. So once you get our next move, so we want to get our next move, and that will be X grid and Y grid. I don't know why it has updated all values of the board to X. That is not right. Wait, what? I'm not sure what that is. So this is 0, 0. And then we are updating the board. I am not sure what is happening here. I'm really unsure about what is happening here. So somehow, so maybe I can do a little bit of something. I can just make move. Can just do a make move function that takes self and then takes our action. I just like to separate something here. Maybe before I can debug, so that I can see. So you can have all this coming here, all this logic coming here. So I'll have X grid and Y grid from our action. Alright, so here I'll be doing self dot make move action. Action will be X grid and Y grid. Right? Then I can do the same here for this. So I just call this action, and then I'll say make move. Sorry, I just saw an opportunity here to reduce writing the code twice. Then now let's try to debug this. I'll just close this one. Let me run this again. Oh, cannot unpack non-iterable object. Really? So there's that error. So I'm not sure why we are experiencing this issue, but maybe I know why. So we have this onUpdate function that seemingly should run. So maybe we can check the documentation. So arcade. I need to know about this onUpdate function, because maybe it's ideally supposed to happen every loop, but now it might be, let me see the manual event loop. So onUpdate provides a hook to update state, which needs to happen at a roughly regular interval. The update event is not strictly paired to the draw event, but they share the same thread. This causes a bottleneck. Okay. So maybe what we can do, I would like to see how many times this on update is called, because I'm not sure what exactly is happening wrong here. So let's print on whenever on update is called, I'll just print. Let's see. So on update has been called twice, which makes sense. There is something definitely not right here. If I print the board right after I update the move, let me see. What will I get? So this is failing at this point. So action is supposed to be a tuple. Wait a second. This. Okay, let me first solve this issue right here. So we have. Oh, this is so crazy. So we have right here on our action, our make move. So I want at this point where I have our make move, we can, for some reason the action is not, so let me just separate this. I don't know why it's complaining. Ideally it should be able to unpack this. So let me just pass it that way and see if that makes a difference. Cannot unpack non-iterable non-type object. Whoa, non-type object. So maybe our issue is here. Print X and print Y. So X is 0 and Y is 0, which is okay. Then when we come to make move, we have our action. Let me just print this action. I'm not sure why this is complaining. Oh, wait a second. This is happening after a second on update. Right. Wait a second. Or is... Am I updating the board here as the AI? Oh no, I think that is it. I'm passing this board. Right, so, So here when we come to on update, so we get our next move. Let me print the board immediately after we get our next move and see whether the values have been updated. Oh my, so that is our problem. Okay, so now I know where the problem is. So ideally, whenever I'm passing this board right here, it is being updated in whenever I'm trying to perform this get best action, it actually updates the board state. Oh Lord. this is a big issue when it comes to Python and the scope of an object. So it's not, apparently we've passed by reference. So let me just do a quick check, just a reminder. Let's ask ChatGPT. When does a parameter passed in Python cause get updated within the function? Huh. Let's see what we have. So whether the object is mutable or immutable. So if it is immutable, then it can be updated. And our list of lists, our dictionary, or a set is mutable. Right. So that means when you're passing this as a mutable object, it gets updated. Within this get next move function, we are updating the board value, and that is not okay for us. So what we'll do, we'll just need to convert this into I'll just call this current board, and I'll make it. So how do I do this? Because when you're getting a board state, definitely you're not updating it. So what do? We can copy this board as current board, and then now that's what we use whenever we are doing this. So when you're getting possible actions, we send the current board. So we might actually be running into the same problem here. So when you're getting possible actions, no, we are not updating the board. And when we get the best action, let's see, when we get the best action, are we updating the board? Let me see. So when you're getting the action state here is when we actually update the state of the board, right? So when we get new board here, we just copy rather than actually updating the new version of the board. So let's see how that works out now that we're copying the state of the board rather than, oh Lord, still the same thing. This is crazy. We're copying the state of the board. So where is this being updated? So we're getting our next move. Then we get the board state. Right? And only passing the current board. Sorry, maybe it's this copy that might return a shallow copy of the list. Huh. So let's see what the documentation says. Actually, might just hover over this. Return a shallow copy of the list. So maybe you can just ask here on ChatGPT how to create a new list from an old one that does not update the old one. I hope that makes sense. So to create a new list from an older without modifying the original list, you need to copy the list. There are several ways to do this in Python, depending on how deep the copy should go. Okay, so if this is the old list, then you can use the list constructor. Basically, that's just creating a new one. And then there's the copy method, which somehow has not worked for us. If the list has nested objects, use a deep copy. Aha, okay. I think this is what we need. We need a deep copy, so recursively copies everything, so even the nested lists are new objects. Right, so that's what we needed. Learned something new today. So here we can go to deep copy. It seems there's no provision for that. So deep copy a list in Python. I'm not sure why we don't have. So this is copied. Oh, you need to import copy. Like, okay, that is interesting. So just out of curiosity, I'm not sure if this would work. So let's say if doing this, creating a whole new list will actually work. I'd like to see if that works. Actually, we might not need this here very much. So just pass both as it was before. However, now get best action, since this is the point where we are actually is it? No, when we get action state is actually when we need to copy. So let me see if at this point so this does not help. So let's just do the deep copy way. So import copy and then, whoops, not in the main method. This should be right here. So we say import copy, and then on our get action state, then here we'll do our copy, that's deep copy, and then we deep copy our board, right? And then that gives us a new board. So let's see if that works now. Aha, perfect. So now that works. You can see our on update function is being called on every game loop, and now we are able to play. So just remove this print right here. Just make sure you remove this print so that we don't feel, excuse me, so that we don't feel our terminal. Same for this. So now if I play, I have an AI. Okay, well, something is happening wrong here. So here I've made my move. But it seems not to be taking. It's not updating. Okay. So it's okay, it's tag print action. So we go to self.makeMove. So we have, I'm not sure what's happening here. So somehow our makeMove function is being called every time after now the user has played, which is me. So what I'd like to see is what is happening. So you have self to make move, right? So every time we're making a move, let's print our so the current player, and then you can print the action as well. Um, so we have X played 0-0. Oh, why was it not behaving before? That is very weird. Okay. So I can see X is playing 1-0. What is 1-0? Wait a second, is this thing not updated? I'm not sure what's happening with this. So, let me try that again and see. So X has played at 0-0. Oh, it's stuck playing 0-0. So we started at. So I'll just close this so that we can start viewing. Let me just play that again. I need to see what's happening again. So what's happened here? So we have X playing 0-0, that's the AI. Then I played 1-1, and then X tried to play 0-0 consistently, which means X did not get the updated board value. That's why it's still trying to play, because basically it will still try to play the first available position on the board, right? So what does change player just swaps? Okay. So now it seems our board has not updated on time. So if I go back to on update, so self, if it's the turn of the AI, then let me do self dot. Sorry, this should be, I just want to print the board and see how it looks like. So if I run this now, so our board is represented correctly. So if I stop right there, we have X, none. So our board is represented correctly, right? That basically means if, oh, right. Interesting. So let me just scroll up. I need to see this. So we started with X, with everything being none, then X played at 0-0, then O played at 2-1. But then when it comes to this representation, what happened is, right, that's the problem. So whenever we are actually placing our play, whenever we are actually making our move on the board, it seems that the way we are representing our board from the AI perspective is kind of shifted, right? So so I'll just transform it. So since at this stage right here, we're using X grid and 2 minus Y grid, then that's what I'll do on the AI side. Whenever we're representing actions, so when we get possible actions, we go to get possible actions. So what I want to happen whenever we're getting these possible actions, what we'll do is we'll use 2 minus y, right, to represent our board. Ideally, the reason why we're doing this is basically because um, when we are rendering, our board is flipped. So you can see now that we've changed. Our board was kind of flipped in terms of rendering. So that's why we're using 2 minus y, so that in our rendering, it represents the position that we actually expect it to be at. So now, this should actually solve our issue, but we get the same issue. Let me just run that with a clean terminal so that we can see. So let's see if this is represented correctly now. So x played at 0-2. X played at 0-2. Oh my goodness. So that did not fix the issue. Actually, what it did, we found ourselves in a bit of trouble again. Right, so the issue is just representation of our board. We're not representing our board accordingly. So x played at 0-2, and ideally 0-2 should be... No, this is not right. X played at 0-0. Okay. So if the issue is representation, then... okay, I think now I know what the issue is. So here on mouse press, when we are looking for our grid position, we're looking relative to the way we've rendered, and that's why we needed to do this this 2 minus y whenever we're making our move. Okay, so that gives me a bit of clarity. So I think what I'll do is I'll just return this. Whenever we're making a move, it will be a bit different for when we're doing it as a player, sorry, as AI, and as the normal player. So here, instead of self.make move, we'll just do this, and for this we'll just use x and y as they are, right? And then also when we come back to this, when we're looking for our possible actions, we'll keep y as is, simply because this here was an issue of how we are rendering versus how we are representing it in our code. But since the AI is not dealing with rendering, it's easy for us to just represent it as is. So hopefully now this works. Great, awesome. So now it worked. The AI even played the next move. So boom, X has won. So the reason X has won is simply because it is playing with the next possible move. Since our Q table is only filled with zeros, it will only fill that. So what I'll do as well, so now every time I play, how will we do this? So I also want that every time I exit, or maybe every time I play, let me just update the Q table, or rather self.ai player.save Q table, right? So I want the Q table to be saved so that you can also view how it looks like whenever we're playing. So we have that. So 0 has 1. Nice. Um, yeah, so let's look at this Qtable now. We have this brain.json. Just remove that. So this is how our JSON looks like. Right? Very interesting. Um, maybe I can just add an extension here for JSON so that we can view it a bit easier. Beautify JSON. Let me just install that very quickly. So as it's doing that, so if I view JSON, so you can see it's representing every state and there's a value for every state, and that's basically how our Qtable will be working. And now every time that we load our AI, it will be loading this Qtable. On every play, it will be updating the Qtable as well, which is, or rather, it will be saving our Qtable. So now we'll be able to save every kind of state that we get. Now, the other thing that we also have to look into is how do we update our table, right? So our Qtable, that is. So every time that we evaluate whether the player has won or not. No, actually, let me see. Yes, so every time we evaluate whether our player has won, um, so at the end of this, we have so if we have a vertical, horizontal, or diagonal match, that basically means we've won, right? So that means we need to check here. There's a player who has won, right? So we need to check if the current player is the AI, right? Self.ai player what is this called? We call it a value representation, right? Value rep. So if it is the AI that has won, then we need to update the Qtable with that win, right? So we'll say self.ai player dot update Qtable, and what we need to pass is the current state of the board. So I'm not sure if, because okay, so here we need the previous state of the board, right? At the moment, the previous state of the board is not saved, right? Because we only check if the player has won after the fact, right? After the move has been registered on our board, right? So what I can do is I'll just make a quick something self dot previous board is equals to self dot board, right? So now we'll have this previous board being saved as well, so that we can see the previous state. So here, every time we're going to update our board, we'll just make self.previous board as self.board. And again, also down here, we'll also save this just before we update the move of the player. And so that means when you come to has player won, when you're updating Qtable, the Qtable we have the previous board, and then we have our action. So you also need our previous action. So I'll just save this. I know there's probably a better way of doing it, but for now I just need I just need this to be working. So our previous action will be none at the moment. then every time that we are moving, whether it's the player or so self the previous action will be X and Y, right? And then when you come down here, self the previous action will be X and 2 minus Y grid, right? X grid and 2 minus Y grid, right? Yeah, so that is the representation that we get. So now when we come back to has player 1, let's go back to this. So we update the Q table with the action that has been played. So that will be the previous action and the reward. So in this case, if it is a win, then so I'll just import these values. So from this AI, we had saved our states. So we have win reward, lose reward. So win reward, lose reward, and draw reward, right? Or rather, actually, I'll just update to this to no reward, right? I think that will make more sense given something I'm just about to do. So we have no reward. When you come to no reward, so if it's a win, then we have a win reward, right? That is if they match, right? If they don't match, actually I need to see whether we have, how do we know whether we've lost? Has player 1 is either true or false. So that is if the player has won. So now let's see self.change player. Okay, so when do you evaluate if the player has lost? Oh, okay. We actually don't need to. So in the game, you only need to evaluate whether the player has won. We don't need to evaluate whether the player has lost, right? So for the AI, we need to know when the player has lost, right? So in this case, has the AI lost? So the AI will only lose if it's the other player who has won. So else here, we'll update the Q table and say self dot previous actually we'll just copy this exactly as is, right? And then now it's a lose reward. And so if none of this happen, then there's no reward. So we also update our AI again that there's no reward for you, right? Yeah, that should be it. That should actually update our brain or our AI. So I'll just change this train to true, right? So at the moment when our AI is picking the best move, so if I come back to this, when our AI is getting our next move, it will be picking the let me see. So when we're getting our next move, when it's getting the best action, at the moment all possible actions are just zeros, right? So it will only pick the next available slot, right? So if I run this, um, you can see that it has picked the first possible value. When I put 0 here, oh, we seem to have an issue. Let me first fix that. So get action state, new state, key error. So get action state, get board state. Okay, so whenever we're trying to get a new board state here, so ideally what has happened is we've gotten a new action state at this point, right? So there's a new action that was not logged before, but we have not saved this state somewhere. We have not saved this state in the queue table. So what we need to do as well here, if not new state in the queue table, then we need to add this new state and assign it our initial self.initial state value, right? So in case we get a new state, we'll always initialize its value to 0. So that should solve that. Anyway, so going back to this issue that I wanted to resolve. So the AI currently will pick the next best move, but the next best move will be the next available move at the moment, right? So it will just pick what is available, right? And that becomes a problem. Okay, I can see we also have another error here. Right, so I'll also need to, now whenever I'm updating, I also need to do it for the current state as well. If we don't have a current state, then we assign the current state as initial value. Right. So going back to the problem that we had before, so now that we have this issue right here, then we need to be able to, like, basically in this training, what I have in mind is if the AI is basically picking sequentially, then it will not give us the best training simply because it will not try out some positions. Like, for example, it will never try out this position right here, right? So what I would like to do is, if you're doing training, what I want it to do when it comes to picking positions, I would like for it to pick positions randomly rather than sequentially. That way there are more chances for it to try different places so that we can have something else running, right? Something else, other values being possible, right? That way we'll not have a damn AI, right? So it's basically, I don't know what I'm doing, so let me just pick any position that is available, and then now we assign our value as we go on, right? So what I'll do here, coming back to this, so when you're getting the best action, so if we are doing our training, so if self.train, then what do I want to do? I want to randomly select an action. So how do we do that? So random is cut. I think we import random. Right. It's been a while since I did this. Random. Is it rand int? Yes. So you want a random integer between 0 and the size of our tuple, right? So we have the length of possible actions. And then I've just noticed here that our rand int will take both, when it's taking A and B, it's including both endpoints. So that means when you get the length, we also need to minus 1 so that we are including each individual position that is available, right? So I want the selection to be random when you're picking our best action. So selected action will be this. Well, let me just update. The best action would be, so this will be the best value that it is. And then the best action will be now our possible actions at the best value, right? And so that's how we'll pick our best action. Whenever we are training, we'll pick our best action randomly, right? So now when we play as we are training, we'll see that now it's not picking the first one anymore. So if you can see, it's just randomly picking positions. So X has 1. Great. So let me see what happens with this. So if X has 1, that is the AI has 1. So now you can see at the end here we have a 0.5 assigned, right? We have a new value assigned. Most of these are 0 values, but at the end of it we have a 0.5 assigned. And this 0.5 is basically showing that this action is positive. Basically, we can win with this action. So let me create a scenario where maybe the player wins. So hopefully, nice. So 0 has 1. So if I go back to this JSON, we should probably have a negative value somewhere. Nice. So we have a negative value simply because we have now, this is a position where our AI has determined that when you reach this stage, then it means we're losing, right? So this now matters. It matters a lot, and it influences the positions. So whenever a certain position is reached, as it evaluates the next actions, then it will know that we need if it's a negative value, then this is not the best course of action. If it's a positive value, then this is the best course of action for us to get there, right? So I'll share a snippet of this in action. So ideally, you can see that for this to work, you have to train it for a while. Like, it needs to be trained a lot. Basically, it needs to play a lot of games so that it can continue with the training. Basically, you need to play a lot of games with it. So the best way would probably be to match the AI against the AI so that it plays against itself. So what I'll do here, so that I can do quick training, right? So what I'll do for this, so I'll just create another AI. So let me call it second AI. And this one I'll just be using for the purposes of training. So our value rep for our AI will be 0. O, of course, plus 0. And then you can say train equals true. Or actually, no, actually we'll not use this one for training. So this one will just be used for playing, right? And then, let me see. Actually, let me just use both to train, right? Now, if you're using both to train, then maybe we need, so we might need a way to mitigate, simply because we have our Q table is loaded for each instance of the AI, right? But now when we train, when we train, when we're training the first AI, we also need the Qtable to be accessible with the second AI as well. So what I'll do here, so I'll change every instance of Qtable to Qtable, like so. And then we'll have Qtable as a global value, right? And then, so every time it is loaded as is, so that basically will mean both AIs will share the same Qtable and they will be updating the same Qtable at the same time. And that saves us a lot of time, right? So the other thing I'll do as well, so I'll also have a variable of whether we're training or not. So if train in the main game, so self.train equals true, and now this is what we'll pass here. Also, if self.train will only have this second AI if we are training, otherwise will not have and the self.userPlay maybe none. So otherwise we'll have that. And then for the second AI, so we'll come to update function here, and you say if so if the current, else if the current player is the self.ai player. So we have our second AI, right? Then we can do everything that we've done here, except now it will be for the second AI. So we have our second AI doing all this. So we get the next move for the second AI, and then we save the Qtable again through the second AI, right? Yeah, that should do it. So if I run this now, hopefully we'll see the AI pitting itself playing against itself. So you can see X as 1, nice, X as 1. So every time it will keep iterating through. Now we have a problem here, empty range in run range. Oh, okay. So now we have an issue here as well, where, so this is, what if there are no possible actions? So what will be the next move? We basically don't have another move, right? Now the issue with this is, let me see. So here, once we has player 1, we change has player 1, then right, so we come here and we update to game view. So now in the case where we are training, ideally we don't want to exit, but we want to reset the whole game again. So what we can do in this case, if you're training, then if we're training, then rather than do all this, what we'll do is we'll reset. Sorry, so this will go into the else, right? So in the training, we'll do a reset. right? And so there is a default reset function. Let me see. So a reset function. Reset the game to initial state. Do changes that need to restart the game. So when we are restarting the game, what we'll do in terms of restart, we'll just we really don't need to change much. We just need the board to be cleared, right? So we set the board to the initial state again. And so now if I run this, okay, so it was playing with itself. Um, so you notice this is crashing every time. So the possible, we can see that the issue is we have a run range of 0, 0. Oh, right. So so if we have an empty run range of 0, 0, that basically means that our possible actions only had one value. That means the only selection that we have is one possible action. So if there's only one possible action, then we don't need to really evaluate all this. So this I'll just put before. If the possible actions, if we only have one possible action, then return that single possible action. That is our only best action. We only have one play to make, so that's all that we'll have right there. So I'll run this now. Let's see. Okay, so list index out of range. So now ideally we have this success where we've managed to so the first instance we had where there was only one possible action, right? But now since we're playing with AI, then that means the next play will have filled all possible actions, which means we'll not have any possible action simply because all the sections in the board are filled. So that is why we're getting this error, list index out of range, right? Wait a second. No, that doesn't make any sense. Let me just print possible actions at this point and see what happens with that. Oops. Oh, right. I'm supposed to run this. Right, so when you're getting this error, let's see, possible actions, we only have, but we have 1, 0. So what is the issue? Oh, right. Wow, such a dumb error. It's possible actions at 0, right? So if I run this one more time, right? So now it's going well, but now we have this issue where we have empty range in run range, right? So basically we have 0, 0 again. And now the reason we probably have this issue again is we have no way of knowing that it's a draw. Do we? Let me see. What happens when you have a draw? Because so when you check if the player has won, I don't think we have a way of checking whether it's a draw. So I think we need to change that. Actually, no, there should be a way. There should be a way of checking. If it's a draw. Pardon, I wrote this code a while ago, so let me just see if I... if I had a draw. So this is Pov's view. We have game overview. So we only have when this player has won or the other player has won, but we don't have a draw. Okay, when we have someone has drawn. So what do we do when, how do we know when there's a draw, right? So if there's a draw, the only way we can know is no player has won, but still the board is completely empty, right? So what we'll do here is if so if the board, so how do we check if there's a non-value? So for actually what I'll do is, given up here we already have these loops that are checking for this any match. So a loop, we can have all field equals false. So all positions field equals false. So as we're looping through here, we can have if this is goes current player, else break that, and then let me see. So ideally what we'll do here, if not self.board at x at y is equals to none. So if we have any that is equal to none, how do we do this? So I'll assume that all are filled fast, right? And then if there's any that is not none, then all field changes to false, right? That's the way I'll do it. And then now here, coming down here, we can have if let's see, if all field, right? If all field, then that means it's a draw. So that means we'll need to do a reset. However, I'll do the reset after updating the Q table, right? Yes. So this will be if all field and no, if all field, then if we are training, then all we need to do, so all we need to do is reset. Otherwise, if you're not training, then all we need to do here is you have a game overview again. Yeah, I think I need to just pass whenever it's a draw. Self.draw equals draw, or let me say is draw, so that it, and then here I can have if is draw, if self.is draw, then we can copy this. So for those who don't understand this, basically, um, this is just the text that will display uh, whenever it's a draw. It's a draw, right? So I'll just put that there. Right. So now we're able to tell whenever it's a draw. And in the case when we are training, if it's a draw, it will also reset. So now we'll not have this issue where we're ending up with an empty range simply because the whole board is filled and we don't have any more options, right? So if I run this now, so you can see our AI will just keep playing with itself. So this is a rushed version of it, obviously. Um, if we look at our brain, so I'll just stop our application here. So if you look at our brain, you can see several values have been given. So let's try and see whether our AI is playing a bit more intelligently with the little training that you've given it. So I'll just change this to false, and then now we can play with the AI. Okay, so we have game view object has no attribute second AI. Okay, right. So I'll just make sure that we are only trying to check for a second AI if we are in training. Otherwise, we do not need a second AI. Right, so now we can play. So you can see X has chosen that position. Look, it's going to win. Then, Okay, so we have another error. If self.isDraw. Right. My bad. So let's play that again. X has won. Nice. So our AI is actually working. What will be the next best move? Let's see if it will. So making dumb moves deliberately, of course. Our AI is not that great. Oh, well, seems like it is smart enough to know when to win. Look at that. Oh, I've won. So ideally, the it does not know how to defend, but it will learn. So in terms of defense, so you can see, let me just play that again. So in terms of defense, it is not the best. So you can see the best would have been putting an X at this position right here so that O doesn't win. However, it has not made that move, and that's where the negatives come in. So if at the moment it's evaluating the best possible move to win, but it's not evaluating which move can make me lose. So that's part of what Minimax algorithm should be. You can check that out on your own. So Minimax algorithm would basically look at, I'm looking at the move that will make me win, but at the same time, I'm trying to prevent any move that will make me lose, right? So that will make it a better AI. But in general, here we have an AI, and you can see if I make any dumb moves, it will definitely win. But if I make if you give time to training, then this AI will definitely perform a lot better. If you just run the training for a longer while, then definitely it will play a lot better than it is right now. Yeah. So basically, that's it. That's how you create an AI. This has been such a long video, but it's ideally me doing raw development. Basically, as you can see, you've seen the way I've been researching how this is basically how you would do it in a normal working environment. This is how you would look at a problem, try to debug it, and just dig into any issues try to resolve, look at what formulas can you use so that you can um, uh, learn or train your AI, or whatever objective you are doing. You really need to do your research as you're going along. Sometimes you don't have everything in your mind, so that's part of development. Yeah. So I really hope you've enjoyed this session. I'm sorry for the way it's long, but hopefully you've also come into knowing how you work in the industry. Ideally, when you have um, when you have worked on something for a longer time, then you find yourself, you really don't need to do a lot of research back and forth. For example, if I had done a lot more JSON stuff a lot more frequently, then you'd find that doing JSON functions will not need me to go for a reference. And that's how you become a better programmer. And also, that's how you use your AI, especially if you're learning. The best way to use your AI is um, use the AI to help you understand what it is you're trying to achieve. Like for example, here I use ChatGPT in order to learn how to make an AI in the first place, and also I wanted to understand how the AI works. So as you can see, the Q table is not so complex. Yes, there's that formula, but it it generally, as long as you generally have an understanding of how it works, then you become a better programmer for that. And that's the best way to use your AI. So I hope you've enjoyed this one more time, and I hope to see you in the next one.